is just what you'd write in the ordinary Copenhagen quantum mechanics as the average energy of the particle. So it's the average energy of the particle, the average potential energy of the particle, and this thing which looks almost exactly like the average kinetic energy of the particle, except this grad is on the wrong side. But if we integrate by parts, you can move that across. So actually, you could even write this if you want to as literally in Copenhagen. What we know in Copenhagen would be the average Hamiltonian equals average energy. Okay, so it's the same thing. It's the same old equation that we had before. So varying. So now that we have a complex variable psi, instead of these two real variables rho and s, instead of having to do two different Euler-Lagrange equations, we can just do one, and we just vary psi star, and it gives you none other than h bar squared over 2m del squared psi plus v psi equals h bar d psi over dt. Okay, so we got the Schrödinger equation. Okay, so it came from varying. So it came from asking that the average Hamiltonian was equal to the average energy,
which is equal to some information.
Well, it's equal to a classical Hamiltonian plus some information. So I mean, you could argue that the classical physics is somehow just information too, but like at the most conservative level, it's what I just said. So, but yeah, it's completely dependent on some kind of information theory, which I don't really understand. Yeah. But I just wanted to wave my arms at it. Okay, so this was basically what Schrödinger did. So I haven't really done anything new. The really suspicious bit was when we included this new complex S. There was no reason to do that whatsoever, as far as anyone can see, really. So David Hestinus, who has this philosophy that the I in not just a philosophy, but a full-blown mathematical framework in which the I in the Schrödinger equation is not a complex number, but a bivector. So it's his picture of I is that it is something that squares to -1, but it's not something that refers to some abstract complex plane on which this psi lives, but rather something that refers to an actual plane in actual space, in real 3D space, about on which the particle is somehow rotating in some way. Okay, so, or said in a slightly more Lie group language, it's I is a generator of rotations, and we're going to take instead a generator of rotations in real space instead of a generator of rotations in complex space. So, but the key thing is that this circulatory motion that we're considering is inherently unobservable because it's associated with the fact that we can't pin down where the particle is. And I think David Hestinus seems to think of it as something like a point particle doing a corkscrew motion, but I actually have a different picture in my mind which may or may not turn out to be right, which is more that a point particle when it flies along can't really have anything resembling spin angular momentum, unless it's in a very peculiar potential, but typically it can't. And also we remember that we wrote the momentum as grad s, which means it has no rotation as a vector field. It has no rotational component. It's just like the electric field in Maxwell's theory. So the new idea was that a point particle can't have this spinning motion, but what can is a set of particles, or a blob, or a fluid. So
a prion. It's a prion composite particle from Abdus Salam and Pati. They invented that just before they invented the Standard Model and won their Nobel Prize, and it was rigorous, it was out there, and then everybody went back to the point part, the dimensionless point particle.
Well, that's an approach that I would also like to look at, but what I was actually thinking something perhaps even more primitive, which is just that now that we're thinking of this particle as being on many possible trajectories at once, we can think of it almost as like a system of particles. And a system of particles can have angular momentum because they can spin around each other. So they have a center of mass, which is in this case is like the average position of the particle, and they have deviation from the center of mass, and they can spin around it. And so now that we've said that the particle is somehow delocalized in space, and not only that, but we've said that that delocalization is real and physical because we attribute energy to it. Now that we've done that, we could say that the particle has a kind of angular momentum.
Absolutely.
And let's not forget that the term we added onto S, not only does it look like a bivector, like angular momentum, it has units of angular momentum. It's h bar.
But so, you should know that your idea is exactly the Abdus Salam and Patti model.
Oh, really?
What they say is that there's no evidence for an electron being a dimensionless point. It's just an abstract thing that got popular. And so the preons are the point. So in other words, they say that an electron is made of some number of point particles called preons in their model, and the preons therefore can have literal spin, the geometric spin.
I see.
And
maybe that's.
And they have a center.
I should definitely check that out. So that sounds like
to start with the Wikipedia article is a great place to start.
It sounds like that's very similar point. So another interesting clue is before. So let's say we're in the 1920s and we don't know anything about this. They had this before quantum mechanics. They had what they called the old quantum theory. And in the old quantum theory, if you did a loop integral of the momentum in space, this was their rule. You get an integer multiple of Planck's constant, or 2 pi of h bar. So this, if you do fluid mechanics, is just the circulation of the momentum field. So it's basically saying that the momentum field does have a circulation, and it's proportional to h bar, which is exactly what we just added in. So, I'm fairly convinced that there is a way to interpret that I as a rotation of the particle in some plane orthogonal to its momentum, a real plane.
Absolutely.
But the thing is that ultimately the theory is indistinguishable from one where you interpret that rotation to be the rotation of the phase on the complex plane, because you can't see this you can't see it. So whether you choose to model it with an abstract complex plane that follows the particle around, or a plane that's somehow in real space, it doesn't make any difference, at least calculationally. But
so there's actually an experiment that's been done. This guy in France did these electron channeling experiments. So electron beam channeling is when you have a beam of electrons going through a crystal material, and the electrons follow a line in the crystal lattice, and they get trapped in little helical orbits around a particular lattice line. And that's called channeling. So if you line up the beam appropriately, a lot of the electrons will scatter, but a certain fraction will get trapped in one of these channels, and then you can see the pattern at the end, and you can clearly see this pattern demonstrating the channeling effect. And this guy thought, well, so the frequency at which, according to some of these theories, at which these electrons would be circulating, if it were a real bivector plane, as you're talking about, the frequency is extremely high. It's about 10 to the 23rd hertz or something. So that's a frequency of oscillation that we can't typically access in a normal experiment. But he thought in a channeling experiment, if the electron, because you have these periodic array along a lattice, and if the oscillation of the electrons themselves, so there are two kinds of oscillations that are going on. On the one hand, there's the actual orbit of the electrons as they orbit around the crystal channel. And secondly, there's the possibility of this high-frequency oscillation or orbit for the electrons in some physical plane that has to do with the IH bar. And he thought, well, there should be some energy at which those two circular motions will be resonant, and we should see a resonant effect in the channeling experiments. And he calculated the energy, and he did the experiment, and he saw a resonant effect. So it's
It's pretty good evidence.
Yeah, so
Can
that's
you give
interesting.
me a reference for that?
Yeah, I
afterwards?
can.
That would be
So,
really
so
important
Mia,
to look
just to add, you guys are probably getting sick of me talking nowadays about the combination of the stepwise spherical Hamiltonian circuit in patterns in a prion model like the QSN. But there should be two foundational classes of particles, okay? There is the prion composite, so it's some quantity of dimensionless points, okay? There should be one pattern that has a discretized spherical rotation, but discretized.
Okay.
And while it's doing that Hamiltonian circuit to complete that with its prion points, it can also have a component which is part of a forward helical path, which would be on the Planck scale. So you wouldn't be able to distinguish it between a helical path and a straight line. And then there would be another class of particles in this kind of model, like on the QSN, which would not have, and by the way, that first one would have to behave special relativistically, because in the discretized time, using Clifford rotors or whatever you want to call your actions of your steps, for some number of actions, you must decide the integer ratio of forward propagation to clock cycles. But then there would be another class of particles, which perhaps we can think about as bosons, which would always be moving at a ratio of 100% forward propagation and 0% clock cycles, simply because, by definition of their construction, they do not have a Hamiltonian or Eulerian circuit in this prion view. That's just not what the pattern is. So it always goes forward in a helical path. It's smaller, it's different, it's a different pattern. So what I suspect is that something like the 57 group is the fundamental massive particle, which is a prion model composed of however many points it takes to make the 57 group. And then there would be another simpler construct, which only has a forward helical component, and therefore, at least in vacuum, must always go at the limit for X number of frames.
And what's that one in your model? So one's the 57 group.
I don't know, but I know what they look like. They look like helices. About 4 years ago, me and Fong were obsessed with building with clear lucite tetrahedra. We were building various logical patterns of helical patterns where you take a 5 group of the tetrahedra and then you append upon that a second 5 group and a third and a fourth, and you have this distinctly different kind of pattern that might be natural in the QSN, which has absolutely no stepwise spherical component like the massive particle idea of the electron 57 group. But then we also said, well, is it a 5 group? Does the 5 group share tetrahedra, or is it kissing faces, or is it just a tetrahelix, which would be a phylix in ours, because it would have a 3 or 5 periodicity. So there are a few logical first guesses that one could have, but I sure would like it to be informed by some group theory or some other things that might, like basically we want to be informed by the Elser-Sloan, and that's where we get the idea for the fundamental massive particle as the electron. We just get that from Elser-Sloan, but we haven't thought or talked a lot about, well, are there any other patterns in Elser-Sloan that might be your fundamental boson, your photon.
I see. Yeah, I didn't have that much more to say really, because I have a lot of ideas, and basically following similar ideas to David Hessius and other people, like 1 or 2 other people only really, about how to incorporate this I, but so far, like, I don't have a consistent framework for it, so there's no point in me sharing all those equations, but suffice it to say that there is the possibility of deriving all of quantum mechanics in a logical fashion, where the terms you introduce are things to do with information theory, which if you understood information theory better than I do, you would know what they were, and the imaginariness is a geometrical thing. It's and that this even has really interesting repercussions if you think about gauge symmetry. So what is gauge symmetry? It's the unobservability of the phase of the wave function, essentially. And at least it is from a non-relativistic point of view. And that in this picture translates to the non-observability of like quantum spread outness. Like the fact that you can only see the particle in one place. So it becomes almost like a physical principle, almost like something more similar to coordinate invariance, where you say it shouldn't matter what coordinates I use, and this says it shouldn't matter where the particle is in its cycling round and round, because it's not possible to see it. So nothing in my measurements can depend on that. Yeah.
Or even taking it maybe a little step further, just like coordinate invariance. It shouldn't be, you're going to use some coordinates, but it's arbitrary where you choose the origin, and that shouldn't make any difference.
Right.
With a phase, if it's a rotation in this bivector plane, you're going to use some direction that counts as angle 0.
Right.
But that's completely arbitrary. So the actual phase itself is no more meaningful than an actual coordinate, which is an arbitrary convention. It's the rate of phase change that is the only thing that could be meaningful.
Right. You're right. Yeah.
Well, I'd be interested in trying to get serious about this, because to me the Maldacena conjecture is not even a conjecture, it's a proof, assuming general relativity is correct and assuming quantum mechanics is correct. If you assume those, which you can't prove those, then his math is a proof that there's a limit to the amount of information, and then from that you get these limits on the right side of the equation that we showed from Rovelli, assuming quantum mechanics, and just from Paul Davies, just assuming general relativity, but at the limit.
Right.
And so therefore, if you, for example, were to sort of take those apart and understand Davies' classic equation and why the golden ratio comes out, and you take Marcello's equation and Rovelli's equation, you kind of deeply understand that, then you tie this information theoretic component of this that you independently derive, which is amazing, because it doesn't matter if somebody else did it, you independently kind of thought this through, then you kind of take that information theoretic component and you think about limits. And so you think, all right, so this equation allows an infinity of information to exist in some volume of space, but now you have to restrict yourself according to Maldacena's proof, right? And then in that proof, you can quickly get to understanding this golden ratio and why, and that it's at these certain limits, and then somehow try to bring the golden. I'm not just a chaser of the golden ratio. I have a strategy for that. Because by seeing the golden ratio recast in this quantized version of this information theoretic quantum mechanics, maybe it'll give some of us some insight somehow, either through Ray's matrix realizations of golden ratio that he's found implied in E8, or maybe in some other more geometric way.
Right. Yeah, there's a lot of interesting stuff.
This is important.
So
I have something to write just about this with the golden ratio. So if you rewrite the equation for psi equals square root of rho exponential of is over h bar.
Right.
So if you choose a specific value for s as a function of rho, S equals 2 pi h bar rho over phi with the golden ratio.
Okay. Let me write this down. So
S equals 2 pi h bar rho over phi. Yes, and with this
2 pi h bar
rho over phi. Phi is the golden ratio.
Okay.
So then if you replace, it gives you a square root of rho exponential of I 2 pi rho over phi.
Okay.
And then if you take for rho all the integer 1, 2, 3, 4, 5 and so on, it will define a series of complex numbers, and this complex number are exactly the position during the growing of the sunflower the famous
oh right,
stuff
it's
that
the
you
Fibonacci spiral, which embeds geometrically the golden
Right,
ratio.
everywhere.
So it's a golden ratio constructed spiral,
So you could introduce it somehow.
which relates
That
to, in some sense, pi and spin, right?
Right. Yeah, that's
From a spiral galaxy to the spin of the electromagnetic field or the gravitational field around some rotating preon particle.
right. Yeah, that's cool. Anyway, so some last little comments before I just like give up. So I should say that this term, this Fisher information term, once you, so if I was to rewrite the Schrödinger equation in terms of S and rho again, then this new term leads to a new term in the Hamilton-Jacobi equation, which is what Bohm calls the quantum potential. But in my version of looking at things, this is not a potential term, but a kinetic term associated with some kind of rotational motion.
Yeah.
So and at that point it becomes interpretation, because you can go one way or the other, and like you said, there's nothing to say that Bohm's wrong. And there's nothing really to say that this is wrong either, as far as I can see.
But there could be some other stuff to say that you're right if you can relate it to gauge theory via hyperlattice and algebra.
Right.
If you can build your pattern on either a hyperlattice with its Lie algebra gauge symmetry or a projection of such
Or
lattice.
something. Yeah, exactly. Or something like that. Other comments of interest. So this Fisher information term.
Well, and by the way, like in fluid mechanics, kinetic terms often act as potentials. You know, once you've got, when it's structured in with a combination of other things, you can have some term that's kinetic, but its gradient can produce some kind of force, and so they act as potentials. So they're not necessarily exclusive.
True. So if you plug in the wave function for the ground state of a harmonic oscillator into this rho log rho squared energy term, you get half h bar omega. So it's the zero. So in this case, it's this term that's responsible for the 0 point energy in the harmonic oscillator, which again, it's like that's the most. It's because that's a minimum uncertainty state, and so somehow there's a minimum energy associated with that via the information theory in the way that you're talking about. So it's exactly like that.
Right.
I think I had one more point. No, I've forgotten that.
Could the minimum energy ever be interpreted as the frame rate of the QSN, if there was a frame rate? Like, would the minimum energy perhaps be that ultra-fast oscillating that would naturally come from, because in this quasi-particle view, you have to play your frames really fast, and generally the particle can't remain in one place. It just kind of jitters about one place, but at an exceedingly high frame rate. And so you can never in QSN quasi-particle view ever have something literally at rest. It must always have some notion of 0 point high energy.
Right. So yeah, it gels very well with that stuff. I can't remember what the other thing I wanted to say. There was something really interesting, but I've forgotten it now.
Is it relating to the equation or relating to Richards?
No, it's gone. Okay, but I'm sure I'll think of it again later. I can tell you this. But anyway, yeah, there's a lot of cool stuff in there.
Yeah, brilliant thinking, very first principles.
Almost there.
Yeah, but it's on that desire to question beyond, the axiomatic kind of things where you just start off on other people's equations 100 years later without questioning, right? So this is beautiful.
And you can, I guess, revisit this and have your momentum on a momentum lattice of some sort, discretized. And that's probably closer to the QSN, where you have a momentum field, but it takes values over a lattice.
Right.
Yeah.
Right. So a lot of people have done that, right, on lattices. But to me, anything you can do on a lattice, you can do on a quasi-lattice. It's the same principles.
Yeah.
Yeah, that's pretty true.
Yes, now Piero is introducing the momentum in the E8 lattice.
Right.
And it should be a momentum
And then,
field.
but once you have that, then you have dual lattices though. So you have a momentum lattice, but then you have a dual lattice, and spectrally, these are different.
Right.
When you have the hologram.
Right.
So.